We're going to start into the world of unstructured meshes today. So far we have only been dealing with finite difference. Normally finite difference will be restricted to structured meshes, but I don't have to. You can take Taylor expansion in actually totally random directions. It's possible, a little bit messy, but I've rarely ever done actually. We have started a little bit with finite volume, but so far only on rectangular cells. So today a little bit more random mesh systems. But before we start looking into it, I wanted to show you this it's a control volume upwind mesh philosophy. You have a classical test case here. You have been given the velocity in here, sort of half a cavity, some sort of geometry. And if you look at the velocity field, it goes like a straight line. So it's just constant rotation. But here you could have used any symmetric velocity field around the origo, potential vortex, anything. The velocity field is given. And then you use the advection equation without any viscosity. That means if you send in any profile here with say concentration, temperature, whatever, it should just be transported and then make 180-degree turn and then come out again on the other side. Especially with this velocity profile, it's just stiff rotation. So this is what you should get. Send in a jump in here is called concentration. Then you should hope for this solution on the other side. So now, of course, it's a question, what kind of scheme are you using? Now, if you can recall the pure advection equation, no viscosity. You couldn't use central difference schemes at all. It was unsteady, unconditionally unsteady. So we had to use some sort of upwind scheme. And first order upwind, very diffusive, as you can see from the top. So this is the ISO line, so this concentration, constant, and then a jump, and then constant. And you see how this sharp gradient then gets smeared out of the entire gap actually on the other side. So first order upwind, very diffusive. And then they play around with even more higher order upwind schemes. Quadratic upwind, it really doesn't help much. Fourth order upwind doesn't help. So it's a hard test case, of course, even with so few cells like this, but still almost impossible to get this one correct. Now the authors here, they have of course their own recipe. If I recall correctly, I think this was man and wife. More and more. We don't have that many ladies in fluid mechanics. It's about time we have some more. I think Faulkner or Scam, one of those were a lady. They're very rare. So here's one. This is more. So yes, they actually solved the problem using some upwind control volume system, which is not easy to understand. I won't go through it at all. It hasn't been actually a success, but just to show you, yes, it is possible. So they had to design suitable upstream control volumes to find the logic how this quantity will be transported into the current cell. So they actually got quite good results here. But I mean, this is for a test case, and it has never been used extensively in any codes that I know about. So yes, it exists upwind systems, but tricky. Of course, for us, we have a viscosity in the problem anyway, so it's a Navier-Stokes we are going to solve, not the Euler equation anyway, so we really don't care. It's not that big a problem. More unstructured mesh systems. Now, these examples is still unstructured meshes, structured meshes. They sort of have the same number of cells in two directions, only the directions has been twisted a little bit, but it's still structured. To create such mesh systems, typically what you do is you solve the Laplace equation. Think of it as potential theory flow, not viscosity. Just solve the Laplace equation for the stream function and the potential function. And you have the stream lines and potential lines. And what's nice here, you will have an angle of 90 degrees on all the cells. So they will still be perpendicular, which is, in many schemes, quite essential actually. If you don't have it, then you will have something you have to adjust with the transport in and out of the cells. But still structured meshes. But now we jump to totally unstructured meshes. Structured meshes will be more efficient when you do the programming, CPU, so it will run faster on any computer, but sometimes we have no choice. We have to use really messy grid systems. So here is a couple of chapters I stole from a book, and the authors here. It's also Patankar, the old famous guru when it comes to finite volume. Now the chapter is called, as you see, Finite Element Methods, number 2. They call it a control volume finite element. I call it finite volume. So I'll show you why later on. The essential part for you, I would say, actually mostly this one. Have you understood how you solve the Poisson equation? You understand the rest as well. We'll talk a little bit here about convection diffusion, when you mix velocity and pressure, and also when we introduce time. But the basic part here is the first couple of chapters. But this actually will be a recipe that you can take in your hand and start programming it. See if I can show you some demos later on. Yeah, the introduction we skip. So we start easy on the conduction type problems, meaning we have a double derivative equal to 0. And here again, the standard Patankar notation. You have a generic unknown phi. You have a generic transport coefficient, large gamma. If you think in terms of what we need in the end in Navier-Stokes, of course, phi will be a velocity and gamma then the viscosity. Here we may or may not have a source term, either constant or a function of the solution. Now, to the discretization. So here we have the essence. Here, a triangular mesh in 2D. 3D, you could use pyramids, tetraheders, but normally what people try to do is use some symmetry. So, okay, in the plane, if you have a messy geometry, use triangles. Then when you go to 3D, you just try to expound them directly into the whiteboard here, so that you will have sort of prisms instead. Of course, possible to use unstructured also in 3D, but things get messy. For this system, we put our unknowns, our phi's, in the corners of each triangle, and then we integrate or use the integral form of the basic equation. So we have to make an integral over a certain volume. The recipe here goes as follows. You find the midpoints in each of the triangle sides, and you use the area center in each triangle. So around this point we construct then a volume which goes from midpoint to center to midpoint to center and so on all around. And then we look at this control volume or finite volume. The reason here that I call it finite volume is that within one triangle you have then 3 unknowns, and the only variation allowed in this context here is linear variation, meaning inside one triangle you can only have, say, a flat plane of your unknown. It can only vary as a linear function. Of course, in this volume then you could have several different angles of this solution plane. Of course, you can be tilted anyway with these 6 triangles, but only linear variation then within one triangle. So I will call it finite volume. Using more advanced interpolation schemes, second order or sine waves or whatever, then I will call it finite element. But people still don't agree actually what is what. So the borderline between finite volume and finite element is not clear. For the boundaries, okay, special attention has to be paid. Of course, one might think, but actually when I did this, just tested it a little bit, doing some programming. If I wanted to say have a normal derivative equal to 0 on one boundary, then I found out if I didn't think about this, just forgot that it was a boundary cell, I found the solution perfectly without me interrupting in any way. So if you don't do anything, automatically you will get Neumann condition on the outlet. So that was sort of cute. Of course, if this one is Dirichlet condition, so you know the value there, then it's not a problem. Then you just insert a number, and you don't treat him as an unknown. But if you treat him as an unknown, and if you don't do anything in particular, you will get the Neumann condition. Some notation. The node number I, and then just looking into one triangle, we'll have the face centers A and C close to the center point. Here the geometrical center O in the triangle, and the far side center point B. Same goes for the boundary and also the corner nodes if necessary. So what we now have to do for our basic equation, we have to take actually a volume integral. If you think in 3D, here it's only a surface integral for this area here for our unknown equations. And of course what we are going to do is to transfer a volume integral into a surface integral. In 2D, that will be take a surface integral and transform it into a line integral. So we only have to integrate along these lines, meaning we are only interested in what goes out and what goes in over these lines. That's the whole point. So starting, if you like, it's a good exercise. Start with the first equation that we had, the Poisson equation, double derivative in both directions, and then a source term. And then you use the divergence theorem in 3D to transfer it into a surface integral. Here from 2D, we will then end up with a line integral. And focusing only on one single triangle, the contribution will only be two line integrals from A, the one midpoint, to the triangular center, and then another line integral from the triangular center to the other midpoint. And then what we are integrating is here some J vector dot product with the normal vector. And also per definition, a normal vector always point out of any volume. The source term, there we can't really do anything special. We have to keep him as a volume integral, or in this case here for us, a surface integral. The diffusion fluxes, these J vectors, can now be looked upon as this gamma and then the gradient of our unknown. And then we have to choose some interpolation functions. Okay, for the large gamma, not so important for us. Normally it will be a constant anyway, but it can be something changing with space as well. Still only here stored and assumed to prevail over the corresponding element, so it should be constant. The source term depends on how it looks. If it's a constant, fairly easy to deal with. If it has a linear dependency of the solution, then yes, that's possible to capture. Higher order dependency, then you have to do some special tricks. But normally a source term for us, it's not a big deal. Constant gravity, something like that. So normally not so tricky. So here comes the essence. We choose the interpolation for our unknowns. And as I said, only linear variation. In 2D, fair enough, but still linear. So I call this one finite. Finite volume. Finite volume only. And to find these coefficients then, for each separate triangle, then we need a bit of algebra. Pure geometry, so it's not that hard. Here using the determinant. Here you can see these coefficients A, B, C will be a function of positions, for the corner positions, 1, 2, 3 in your triangle, but also the solution, phi1, phi2, and phi3 enters into these coefficients. That's not something that we like, so we are going to manipulate this one a little bit further. So you will normally treat a triangle like this, a local coordinate system inside in the origo. When we come to the velocities, we might tilt this local coordinate system so that the x-axis goes in the average velocity direction. Remember, you have your unknowns in the corners here. So for the first problem here, the Poisson equation, think of it as the pressure location. But with the velocities, okay, then you have two velocity components here as well. And then the average velocity will then be the sum of all three, and then divided by 3. So here our J vector in general, this is the one we are going to take the line integral of. Here we have kept this gamma as a possible variable. It doesn't have to be constant. And now looking at these two contributions that we have from one triangle, these two line integrals, we will end up on the right hand side with something like this. We're still not home. It's fairly elegant actually, the way you split it up. So remember, you had a dot product here, so sort of in general direction, can be any direction, this normal vector. But this way of interpolating your unknowns, you'll end up with a cute little expression on the other side. It's not that hard. Source term still have to be volume integral. So in 2D, you have the area, and then the linear variation if you have one. And then finally adding it all together. And now we are talking a more useful form. So it's possible then to rewrite our two line integrals, contribution from one triangle for the node point I. You will end up with some coefficients multiplied with all the three unknowns belonging to that triangle, plus a possible constant term. And if you now look at these coefficients, C1, C2, C3, you see they are just geometry. They don't depend on the solution itself at all. It's only coefficients. Meaning you can calculate these C1, C2, C3 and the B1 once and for all for one mesh and just store them. Then of course it's very rapidly to evaluate these fluxes. A little bit memory of course for one triangle. You have these numbers you have to store, but fairly easy calculation. Of course, if you are talking about moving meshes, deformable meshes, then you have to redo this calculation every time you change the mesh. But for a fixed mesh, quite efficient. So in the end, what you will end up with is of course a set of algebraic equations for all your unknowns. So you'll have the sum of all neighbors and maybe a constant term as well. And how to solve such algebraic equation systems, that you are already skilled, you know how to do that efficiently, so no problems. Especially for the boundary nodes. Well, like I said, if you need a Neumann condition, you don't have to do anything. Just treat him as an unknown. If it's a Dirichlet condition, even easier, you just give him a value. Just specify. So the boundary conditions are fairly easy handled here. Well, if you have a Neumann condition, the derivative is equal to not 0, but something else. Okay, then you have to look into the detail here and program a little bit yourself. But if the constant is 0, you don't have to do anything. Fairly easy. So how to solve it? Well, as you now know, when you have a set of algebraic equations, of course, if you don't have too many unknowns, you can solve them using a direct method. But we rarely ever do that in CFD. Normally all our problems is too big, we can't use direct methods. So here we sort of set up an iterative scheme. Remember, we don't have time here, it's only space derivatives. So you start with some initial values, some guess, and then calculate once all these coefficients, C1 to C3, that we are going to need. And then you can set up the equation systems and then solve for all your unknowns. And actually, it's possible here to do it very crudely. I can show you later with a little demo. That if you just think in terms of Jacobi, if you look at one node, and then you just treat the rest as known, just update the value according to your equation system. Of course it will be wrong, but at least you will update the value based on its closest neighbors. And then you sweep over the entire domain for all nodes. And if you have a sort of quite a nice mesh, it will be quite diagonally dominant equation system, so he will find a solution fairly rapidly. So you can iterate here and find a solution fairly easy actually. But then, very big problem, okay, then you have to do something else. Like multigrid, conjugate gradient or something. Let's see if we can make this demo run here. If I have it with me. Here we go. So it's just a quick and dirty program I made. I started out with sort of a very nice structured systems, creating all my small triangles, your nodes in the corners. And then I used more or less a random generator to produce sort of a little unstructured boundary here. Then you needed some interpolation to find out sort of the border elements. I could have used even a more random mesh than this, but just a demo anyway. So sort of an initial system here, giving them random values, and also the boundary cells also are given quite random numbers. So the volumes will now be these, how many are there? 6 filters, most of them at least. And now solving the equation system by the just very simple, primitive, iterative technique. When you solve for one, you will then have contributions from all these neighbors around. You just treat them as known. So it's just one update directly. But as you see, he finds the solution very easy, very fast. And when you have the solution, okay, then you can plot the entire field and here he then plots. Within one triangle you have only linear variation, so it takes sort of triangle part by triangle part within each volume. So as you see, he'll spend, at least this computer, spend much more time plotting the solution than actually solving it. So not uncommon. It's the graphics that takes time. Computation goes fairly fast. So the Poisson equation here, very easy to solve on totally unstructured mesh systems. Yeah, you can just be standing there in the background. Taking it a step further, convection and diffusion. We still don't have time, but now we are mixing with velocity fields. And here, sort of a way to cheat. You know these terms, they are nonlinear. You have velocity times velocity. But when you treat this phi as a generic unknown, at least they look to be linear terms, but they are not. They are non-linear. So on the right hand side, well, we have the Poisson equation, and then we have the advection terms to the left. So now it's of course a question how to handle the velocities. So here the thought of keeping the velocities known, still not a part of the solution. So you're only focusing on the unknown phi, that's all. And then actually do exactly the same, finding the integral form, and then this flux function, the J vector. This one we had already, and now we'll have some additional term for him. But the rest goes exactly as before. We need this velocity then. So here, averaging the velocity within one triangle. So fairly straightforward. And then here they make a point in, as I said, you tilt the local coordinate system so that the x should go in the velocity direction for that triangle. So I've done this because it's then possible to write it in a form using the local cell Reynolds number. As we know, this one then has to be smaller or equal to 2, or else it blows up. Not because of any instability with respect to time, but with respect to space. That's a requirement for space resolution. And here it will be sort of hidden automatically inside your grid systems. So I don't know if it has been widely used after this, but at least it's a possibility. So I don't think it's really necessary, as long as you have enough cells to resolve all the scales. This should be okay. But here they like to do this, so they sort of have this local cell Reynolds number under control. Their choice. So a little bit different then with the interpolation for our known phi, but still exactly the same philosophy. Linear variation within one triangle only. And you will end up sort of with the same system here. You will have in the end some coefficients, then that should not depend on the solution. That's the whole point here. Let's see how they end up. Here you have them. So it's then possible to write these line integrals as some algebraic sum of all the neighbor contributions, and the coefficients d1, d2, d3, and e1 should then just be not dependent on the solution. It's just geometry. So you calculate them once and for all. Here you find them in the appendix. And then again, algebraic equation system ready to be solved. Then we introduce the pressure, and then we are talking problems. When this was written, it was some years ago, so they didn't use sort of the state-of-the-art possibilities that we could use collocated mesh systems. Today that's the most popular, and it actually works. If you can recall, we chose staggered mesh systems when we talk about finite differences in a structured mesh. The reason is we only have a single derivative of the pressure and we have double derivative of the velocity. So if you discretize sort of straightforward, you end up for the unknown velocity u, when you're focusing on him, the pressure where you are standing does not enter the equation system, the algebraic equation system. Hence, you will get pressure fields which will be very, very strange. So sort of in 2D it will be a checkerboard pattern where the white pressure, they don't talk to the black pressures at all. They can be totally different. So very hard to avoid. But modern techniques, they have used this for some years now with some interpolation tricks to sort of couple the local pressure in the same location as the velocities, so that you can avoid this. And this is definitely the most popular. But when this was written, that was not sort of state of the art. So here they use a sort of a staggering idea here. Makes it a little bit messy, but still possible. So here we have our equation system. And now we are talking steady state Navier-Stokes. And we have the continuity. So now we have to solve our equation system. We can even have some other generic equation systems, energy equation, whatever. Phi can be anything, concentration, species, whatever. So the philosophy will be quite simple. You look at the your mesh system and then say, okay, I have the pressure and the velocities in the corners. Start there. But then, if you only do this, you will have this checkerboard pattern pressure solution. Doesn't look too nice. So we create a submesh. I mean, when you have a triangle, it's fairly easy to create 4 triangles out of it. Just use the midpoints to obtain this mesh system. And then you use the fine mesh system there for velocities only. So the additional points here will be additional velocities. The pressure only in the big ones. So that's one way here to sort of create a staggered mesh system, to couple the pressure and the velocities. So of course a little bit more bookkeeping. So now you are talking different volumes, control volumes for either pressure or the velocities. But it works, that's the whole point. So the pressure only in the big corners, velocities and any generic unknown will now be also in the small sub-meshes as well. So that's one way to do it. And well, the rest just follows the same recipe. No problem there. But of course, in the end here, we will have a problem or a question then. What about the pressure? How to update the pressure? So that one is something we will have to look into. So linear interpolation for everything, pressure, velocities, the unknown fees, whatever they are. And you end up, as always, with this equation system. Your line integrals end up with the coefficients, which then should be constants independent of the solution. Lot of coefficients. So here we are talking pressure correction and velocity correction equations, because here it's sort of unavoidable. You will end up with an algebraic equation system which sort of can't be solved. You mix velocities and pressure together, so some way along the line here you have to use an additional equation to solve the problem, and then of course continuity. I'll look into this in the next lecture. Any questions? Then we take a break.